Hello, my name is Sang-Jin Liu. I'm an associate professor in mechanical engineering at the University of Nebraska-Lincoln. So today I present our research on bubble generation during drop coalescence. So drop coalescence is a very common physical phenomenon where two drops make in contact and then they merge. And then this drop coalescence process is driven by surface tension between the drop and the surrounding fluid. So in this study, we have two motivations. The first motivation is powder bed fusion process for metal additive manufacturing process. And this technology has been well studied and also accepted and applied by NASA. And in this powder bed fusion process, a particle of metals are layered in several layers on top of a part, and the laser is shed onto the particles where we want to actually merge them. So that as we build up layers like a 3D printing, and then we'll be able to make a metal 3D part. So during this process, metal powder particles are molten by laser, and then the solid particles become liquid drops, and then they merge, to between drops. And then this drop coalescence process occurs on the surface of the, part being printed. Then as you see here, we expect that the drop bubbles can be created between two drops during the drop coalescence. And then we expect that this bubble creation can be related to the pore generation of 3D printed metal parts. So that is one motivation. And another motivation, the other motivation is enhanced oil recovery. And then this figure shows the schematic figure of the oil well. And then when oil well, once we finish withdrawing, harvesting oils from the oil well, then the engineers can inject hot water or carbon dioxide with detergent or surfactant so that the oil ganglia or oil drops confined between solid particles such as rock or sands particles, they can be moved away by the flow so that we can extract oil with water onto the underground facility so that we can separate water and oil. This is called enhanced oil recovery process. And then as you see here, depending on the surface wettability, whether the surface likes a certain liquid or not, the oils can stick to the surface or can be easily removed from the surface. And then during this process, oil ganglia, oil drops can meet each other and then they become bigger drop, which is also drop coalescence. Then in these two cases, drop coalescence happens with confinement. That means one drop and another drop or multiple drops, they are confined by solid surfaces. It can be just single surface or surrounding surfaces. And then depending on the property of the surface, the drop shapes can change. Then our interest is what is to find out the roles of this solid surface confinement on drop coalescence. And then this research question has been actually less studied compared to coalescence of freestanding drops. And then in Japan, this is my collaborator, and then they studied drop coalescence using this kind of geometry, which is called the helical cell geometry. So as you see here, helical cell geometry is nothing but two parallel surfaces with very small gap height or gap distance. So this gap distance is much smaller than the size of the drop of interest. And in this case, they filled the helical cell with glycerol and oil, and they created another glycerol drop here, and then they let this glycerol drop slide down toward the glycerol bath due to gravity, and then they observed the drop coalescence from the initiation of the drop coalescence and the growth of the liquid bridge. And liquid bridge is the actually connecting part between two drops. And then they measured how this liquid neck grows as a function of time. So then in my laboratory, we conducted a similar experiment, but in a different way. Oh, before that, I wanted to explain the category of drop coalescence. So as I said, many works, most of the previous works have been about the coalescence of two freely standing drops. So then in this case, we call them unconfined drops because they are not in contact with any confining surfaces. But as I showed in powder bed fusion process or in NAS oil recovery process, also in inkjet printing process, you can find many other processes and systems where drops meet each other on a confined surface. And then when those two drops are meeting on a solid surface, and we say them drop coalescence on one bounding surface. Or as I showed in the previous slide, when two drops are coming to contact between two parallel surfaces, such a phenomenon or such case is called the two bounding surfaces. So our interest in this presentation is this one. We have two parallel surfaces, solid wall in the helical cell, and then we have liquid drop and gas, so that we have three phases: liquid phase, gas phase, and solid phase. As such, we have a contact line, as shown here, between the solid surface, gas phase, and liquid drops. In order to conduct this experiment, we made a helical cell geometry using PDMS. I'm not going to spell out this word because it's a tongue twister. PDMS and then microfluidic technology. So you see the schematic figure of our device. So this part, PDMS, is transparent rubber, so that we can actually see the drop. And then the bottom is glass surface coated with PDMS, so that we can have the same surface wettability around the surface, the drops. The gap height was either 220 micrometer or 1 millimeter. And then we created two drops by injecting our liquid of interest. And then as you can imagine, drops grew in the radial direction while their heights are confined or fixed. So they looked like pancakes. And then as they grew, then at some point they made a contact to each other, then coalescence occurred. Then we captured that motion or phenomenon using high-speed camera and microscopy. And then here, the continuous phase is air, as I said, and then dispersed phase, it can be water, glycerol, mineral oil, ethanol. But in this presentation, I'm going to show you result with water and glycerol in most cases. And then this shows our setup. Setup is very simple. Here, well, I'm gonna just click, yeah. We have a PDMS microchannel device, and then you can see two pancake drops growing in the helical cell. And then we use a high-speed camera and this microscope to capture the motion of the drop. And then in this result, I show you glycerol drops coalescing in air. So you see this is air. This is one glycerol drop and the other glycerol drop. And then this number value shows the viscosity of this glycerol, which is about 40 times more viscous than water. And the contact angle of this glycerol drop in air on PDMS surface is shown here, so that we can see that PDMS is a hydrophobic. And by the way, glycerol is a water-based liquid solution. The frame rate was this 120,000 frames per second because the drop coalescence phenomenon is super fast. So then now you can see that the liquid bridge is growing, and then we can see very complicated geometry of the change of the meniscus shape. And then now we see some faint things at the center of the bridge between two drops. So then this is a still shot of the video. You can see that the meniscus of the two drops are twisted, and then we can see the propagation of the capillary wave along the meniscus of the drop. And then at the center, while the liquid bridge is growing in the lateral direction, we see some faint thing at the middle of the bridge. So we noticed this faint thing that we wanted to find what this was. Okay, as I said, capillary wave, and then, oh, yeah, this is actually spoiler. We found that this is an entrapped bubble that I will show you in the following slide. So in order to find what this thing was, we repeated the experiment while we tilt the helical cell with about 10 degrees. And then we captured the motion, and then we found that we focused on the top surface of the helical cell, and then we could clearly see one big bubble and then small daughter bubbles. And then now we moved, so then this is a more zoomed in image after 2 seconds, 2 seconds after the initiation of the drug coalescence. And then this shows the bubble at the top. Now we moved the focal plane over the microscope, then we could see actually bubble on the bottom. So that means we found that bubbles are created on the near the top surface and the bottom surface of the helical cell. So then since we have found that these bubbles are located very close to the top and bottom surface of our helical cell, now we repeat the experiment while focusing on the bottom of the helical cell so that we can see how this bubble is created. So then here you can see that when the neck was formed and the neck or bridge is growing in the lateral direction, now we can see that the air tube was trapped within the bottom surface of the helical cell and then growing neck over the liquid bridge. And then this air pocket or tube is stretched by the growing liquid bridge. So then as a result of that, the air tube experiences surface tension driven instability, which is called the Plato-Rayleigh instability. So you can think about just a water jet dripping from your water faucet, and then it becomes drops because surface tension tries to minimize the surface area. And then as the result, now we can see one mother bubble and then 2 daughter bubbles. And then so here from this experiment, we came up with this mechanism. So what you see here is the side view of our helical cell, top surface, bottom surface, one drop and the other drop. And then now we have this air locating or air between the growing neck and the surface. So then this part corresponds to this air tube. And then as the neck grows, the tube is stretched, but the surface tension really hates that. So then at some point, this air tube breaks down into smaller bubbles. That's how we know that air bubbles can be trapped and created in these merging drops. So in order to confirm our finding, we repeated this experiment on a single surface, and then 2 drops. And then in this case, the drop was more viscous than, actually water, I'm sorry, is a 1 CP. So then now you can see, something is wrong. Actually, this video should work, but somehow it does not work. Oh yeah, okay, now it goes. Sorry about that. So now you can see that the air bubble is trapped and then stretched by the growing neck, and then now we just have only one bubble near the solid surface. Since in this case, we have only one confining surface, that we have only one bubble near the solid surface. So my presentation is relatively short, but here we wanted to share our project supported by NASA Nebraska Space Grant and also American Chemical Society Petroleum Research Fund. So then, as I showed at the beginning, there are many processes and systems in which drops are merged to each other, confined by solid surface, single surface, or multiple surfaces. And then we can recreate such a process in the laboratory using the helical cell geometry. And then we found that since the helical cell surface is hydrophobic, we found that air bubbles were trapped in the growing, merging drops. And then we proposed the mechanism for this bubble entrapment. And then as we continue this project, and then we also tried letting 2 drops merge in vacuum condition. And obviously, as we remove air from our chamber, then we didn't see air bubbles. So that actually experiment supports that the trapped bubble, it comes from the ambient air in the helical cell. Also, we tried hydrophilic surfaces for helical cell. In that case, we could not see air bubbles. So that we now think that this air bubble entrapment is related to the requires two things. One is a hydrophobic surface, so that contact angle is greater than 90 degrees, and also the ambient gas, so that the gas can be trapped in coalescing drop. Thank you for your attention.